Something strange just flew through our solar system. An object from interstellar space, traveling for potentially millions of years through the void between stars, has just made its closest approach to our sun, and what NASA observed has left scientists completely baffled. This isn't the first interstellar visitor we've detected, but it might be the most mysterious. It's called 3I Atlas, and if it's a comet, then it's the strangest comet we've ever seen. Its behavior defies explanation. It got 400 times brighter than it should have. It changed colors in ways that make absolutely no sense. It's accelerating under its own power in directions that gravity alone can't explain. And it's shooting jets of gas both toward and away from the sun at the same time. NASA has been tracking this thing for months now, and with every new observation, the mystery only gets deeper. Some scientists think it's just an unusual comet. Others aren't so sure. And there's a small but growing group of researchers who've suggested something far more controversial, that this might not be natural at all. So today, we're going to break down everything we know about 3I Atlas. We'll look at how it was discovered, what makes it so different from every other comet we've seen, and why some very serious scientists are asking questions that sound like they came straight out of a science fiction movie. Because one thing is absolutely certain, 3I Atlas is not behaving like anything we've encountered before, and NASA knows it. But before we start, make sure to subscribe to the channel. That would really help. Before we get into the weirdness of 3I Atlas specifically, we need to understand what interstellar objects actually are and why finding them is such a big deal. Our solar system isn't a closed bubble floating alone in space. It's actually traveling through the galaxy at about 450,000 miles per hour, orbiting around the center of the Milky Way. And as we move through space, we occasionally run into objects that don't belong to our sun, visitors from other star systems. These interstellar objects have been kicked out of their home systems, usually through gravitational interactions with giant planets or close encounters with passing stars. Once they're ejected, they drift through the galaxy for millions or even billions of years, traveling through the emptiness between stars, where there's essentially nothing. No planets, no asteroids, no comets, just empty space and the occasional stray hydrogen atom. Now, the chances of one of these objects actually passing through another star system are incredibly small. Space is so ridiculously vast and empty that an object could travel for billions of years without ever coming close to another star, but eventually, some of them do. And when they pass through our solar system, they give us an amazing opportunity to study material from another star system without having to travel light years to get there. For most of human history, we had no way to detect these visitors. They move too fast and reflect too little light to be spotted by the naked eye or even by early telescopes. But in recent decades, our detection technology has gotten way better. We now have automated survey telescopes that scan the entire sky every single night, looking for anything that moves against the background of stars, and that's how we started finding them. The thing is, we always knew interstellar objects had to exist. The math said they should be out there. But actually finding them and studying them is a completely different challenge, because these objects are moving insanely fast, typically somewhere between 50,000 and 150,000 miles per hour relative to our sun, and they don't stick around for long. When an interstellar object enters our solar system, it's on what astronomers call a hyperbolic trajectory. That basically means it's moving so fast that the sun's gravity can't capture it into an orbit. It swoops in, gets bent by the sun's gravity, and then shoots right back out into interstellar space, never to return. We get one shot to observe it, and then it's gone forever. That's why every interstellar object discovery is so important. Each one is like a messenger from another part of the galaxy, carrying clues about conditions in other star systems. And each one behaves slightly differently, teaching us something new about what's actually out there in the universe. The first confirmed interstellar object was spotted on October 19, 2017, by the Pan-STARRS telescope in Hawaii. They named it Oumuamua, which means scout or messenger in Hawaiian. And from day one, this thing was absolutely bizarre. First off, its shape was unlike anything we'd ever seen in our solar system. Based on how its brightness changed as it tumbled through space, scientists calculated that it was extremely elongated. somewhere between 5 to 10 times longer than it was wide. Picture a giant space cigar, or maybe more like a cucumber shape. Nothing in our solar system looks like that. Second, it was incredibly reflective. Its surface was really shiny, reflecting about 10 times more light than a typical asteroid. This suggested it might have a smooth, possibly icy surface, or maybe even something metallic. We weren't really sure. But here's where things got really strange. Oumuamua was accelerating, not just coasting through space at a constant speed, but actually speeding up as it moved away from the sun. Now, this kind of non-gravitational acceleration is pretty common in comets because the sun's heat causes ice to vaporize, and those jets of gas push the comet around a bit. But here's the problem. Oumuamua showed absolutely no signs of outgassing. No tail, no fuzzy cloud of gas and dust around it, no detectable emissions at all. Yet somehow, it was still accelerating. That shouldn't be possible. This led to all kinds of wild speculation. Harvard astronomer Avi Loeb famously suggested that Oumuamua could be an alien light sail, basically a thin reflective sheet designed to be pushed by starlight or lasers, kind of like the concepts we've been developing for interstellar travel ourselves. A light sail would explain the weird shape, the high reflectivity, and the acceleration without any visible gas emissions. Most scientists thought Loeb was jumping the gun, arguing that Oumuamua was probably just an unusual comet made of some type of ice that doesn't produce much visible gas when it vaporizes. Maybe it was nitrogen ice or carbon monoxide ice, which would sublimate without creating the typical dusty cloud we see around normal comets. But here's the thing, we never got a definitive answer. By the time scientists realized just how weird Oumuamua was, it was already on its way out of the solar system. No spacecraft was anywhere close to being able to intercept it, and our telescopes lost sight of it as it faded into the darkness. Oumuamua left us with way more questions than answers. What was it made of? Where did it come from? Was it a comet, an asteroid, or something completely different? We'll probably never know for certain. But one thing became crystal clear. If interstellar objects could be this strange, we needed to find more of them, and we needed to be ready to study them properly when they showed up. Luckily, we didn't have to wait long. Just 2 years after Oumuamua, on August 30th, 2019, an amateur astronomer named Gennady Borisov discovered another interstellar visitor using a telescope he literally built in his own backyard. This object was designated 2I/Borisov, the second confirmed interstellar object. And unlike Oumuamua, Borisov looked exactly like what we'd expect a comet to look like. It had a bright, fuzzy cloud of gas and dust surrounding its core. It had a tail. It behaved like a normal comet as it got closer to the sun. In pretty much every way we could measure, it acted like a regular comet, just one that happened to come from another star system. This was actually a huge relief to a lot of scientists, because it suggested that Oumuamua might have just been a weird outlier, and that most interstellar objects would be more familiar and easier to understand. Borisov was also much bigger than Oumuamua. While Oumuamua was estimated to be only about a quarter mile long, Borisov's core was probably somewhere between half a mile to a full mile across. This larger size made it much easier to study in detail. When scientists analyzed its composition, they found it was surprisingly similar to comets from our own solar system. It had water ice, carbon monoxide, and various organic compounds, basically the same ingredients we find in comets that were born right here around our sun. This suggested that the building blocks of planetary systems might be pretty similar throughout the galaxy, at least in our cosmic neighborhood. Borisov's path through space also told us something interesting. Based on its trajectory and speed, scientists figured it probably came from a binary star system, 2 stars orbiting each other. These binary systems have really chaotic gravitational interactions that frequently result in planets and comets getting ejected into interstellar space. So Borisov's origin story made perfect sense. By the time Borisov left our solar system in late 2020, scientists had gathered tons of data on it from telescopes all over the world, and even from the Hubble Space Telescope orbiting Earth. We learned a lot from Borisov, and it gave us a good baseline for what a normal interstellar comet should look like. Which brings us to 3I Atlas, because if Borisov was the normal one, 3I Atlas is anything but. 3I Atlas, officially designated CEAS 2024 S1 Atlas, was discovered on September 27th, 2024, by the Atlas Survey System in Hawaii. This is the same automated telescope network that's designed to spot asteroids that might pose a threat to Earth. At first, it looked like just another comet, maybe from the outer edges of our solar system. But as astronomers gathered more observations over the next few days and started calculating its orbit, they realized something incredible. This object wasn't gravitationally bound to our sun. Its trajectory was hyperbolic, meaning it was moving way too fast to be captured by the sun's gravity. This was the third confirmed interstellar object to visit our solar system. The discovery itself was really lucky timing. Unlike Oumuamua, which we discovered on its way out of the solar system, giving us only a few weeks to study it, 3I Atlas was spotted on its way in toward the sun. This meant scientists would have several months to observe it, prepare telescopes, and gather as much data as possible. In those first few weeks of observation, 3I Atlas looked relatively normal for a comet. It had a faint, fuzzy cloud of gas and dust around its core. Its light spectrum showed typical comet signatures: water vapor, carbon-based molecules, all the usual stuff. Early estimates suggested it was a decent-sized comet, probably somewhere between 3 and 6 miles across. But even in those very first observations, there were small hints that something was a bit off. The comet appeared slightly redder than astronomers expected, meaning it reflected more red light than blue light. This isn't completely unheard of for comets, but it was notable enough to raise a few eyebrows. Red colors in comets and asteroids typically come from organic compounds on the surface, similar to the reddish color you see on some of the outer solar system objects. For an interstellar object, having a red surface actually made sense. After spending potentially millions of years in interstellar space getting bombarded by cosmic rays, the surface material would naturally develop these complex organic compounds that appear red. Then in early September, something weird started happening. The comet began brightening faster than it should have been. Not dramatically faster, but definitely faster than the models predicted. Comets typically brighten gradually and predictably as they get closer to the sun. But 3I Atlas was brightening faster than the math said it should. And then came something really strange. The color started to change. Over just a few weeks, 3I Atlas shifted from red to green. This was unusual because comet colors don't typically change that dramatically over such short time scales. Green colors in comets usually come from specific molecules, diatomic carbon and cyanogen, that glow green when excited by sunlight. For the comet to suddenly start producing large amounts of these molecules suggested that something had changed either on its surface or inside the comet. Some scientists thought maybe the comet had a layered structure, perhaps a dusty red exterior covering fresher icy material underneath. As the outer layers boiled away from the sun's heat, it could have exposed the fresh ice, changing the comet's appearance. This seemed like a reasonable explanation at the time, but reasonable explanations were about to become a lot harder to find. There's something really interesting about the timing of 3I Atlas showing up in our solar system right now. The year 2025 happens to coincide with what we call the solar maximum, the period when our sun is at its most active point in its 11-year cycle. During solar maximum, the sun's magnetic field gets really chaotic and tangled up. Sunspots appear all over the surface. Solar flares erupt constantly. And we get these massive coronal mass ejections, basically huge chunks of the sun's atmosphere getting blasted out into space at millions of miles per hour. This increased solar activity has real effects here on Earth. Throughout 2024 and into 2025, people all over the world have been seeing way more frequent and way more vibrant auroras, the northern and southern lights. These auroras happen when charged particles from the sun slam into Earth's magnetic field and atmosphere. When the sun is more active, we get more of these particles, which means brighter and more widespread light shows. The current solar maximum officially kicked off in October 2024, and it's expected to last through most of 2025 before gradually calming down. The absolute peak of activity seems to have happened in late 2024 and early 2025, right when 3I Atlas was making its closest approach to the sun. This means 3I Atlas encountered our sun at literally the worst possible time, or from a scientific perspective, the most interesting time. The comet wasn't just getting hit with the sun's normal heat and radiation, it was getting bombarded by an elevated level of solar flares, coronal mass ejections, and streams of charged particles. For a normal comet from our solar system, this might just mean slightly more gas production or a bit of extra brightness. But for an interstellar object that's potentially spent millions of years frozen in the void between stars at temperatures just a few degrees above absolute zero, suddenly encountering a hyperactive star could trigger all kinds of unusual responses. Now, you might be wondering if the timing is more than just coincidence. Could interstellar objects somehow be attracted to stars during periods of high activity? Almost certainly not. There's no known physical mechanism that would cause that, but it does make you think. What we do know is that the combination of an interstellar visitor and solar maximum created a perfect storm of unusual conditions. And 3, I-Atlas's response to those conditions turned out to be unlike anything astronomers have ever witnessed. For any comet, the most dramatic and intense phase of its existence is perihelion. That's the point when it passes closest to the sun. This is when the sun's heat and radiation are at their absolute maximum, causing ice to rapidly boil away and gas to blast off the comet's surface at high speed. For 3, I-Atlas, perihelion happened on October 29th, 2024. At its closest approach, the comet came within about 8 million miles of the sun's surface. To put that in perspective, that's only about 1/10 the distance between Earth and the sun, well inside the orbit of Mercury, the closest planet. At that distance, the temperature on the sunlit side of the comet would have skyrocketed to several hundred degrees Fahrenheit, possibly even over 1,000 degrees, depending on exactly what the comet is made of and how fast it spins. That's hot enough to vaporize water ice, carbon dioxide ice, methane ice, and even more exotic stuff like carbon monoxide or nitrogen ice. The radiation environment at that distance is also incredibly intense. We're not just talking about visible light and heat. There's intense ultraviolet radiation, X-rays, and constant streams of charged particles from the solar wind. And remember, because we're at solar maximum, there's a pretty good chance that 3 I-Atlas got hit by one or more coronal mass ejections during its close pass. Each of these CMES carries billions of tons of plasma moving at speeds of several million miles per hour. When one of those slams into a comet, it can strip away outer layers and dramatically increase how much gas is coming off the surface. Now here's where we run into a problem. During perihelion, 3 I-Atlas was positioned almost directly between Earth and the Sun from our perspective. This meant that our ground-based telescopes couldn't see it at all. The sun's glare was way too bright. It would be like trying to spot a firefly right next to a 1,000,000-watt searchlight. But we had 2 major advantages. First, NASA's Mars Reconnaissance Orbiter happened to be in the perfect position to photograph 3 I-Atlas from Mars. Since Mars was on the opposite side of the Sun from Earth at that time, it had a clear, unobstructed view of the comet during its closest approach. The orbiter's high-rise camera managed to capture what will forever be the highest resolution image of 3 I-Atlas, the closest look any spacecraft will ever get at this thing. The image itself isn't exactly stunning. It looks like a bright, fuzzy white blob against the darkness of space, but it's historically significant as the closest view we'll ever have of this mysterious visitor. The second advantage we had was our fleet of sun-watching satellites. Both NASA's SOHO satellite and ESA's STEREO spacecraft carry special instruments called coronagraphs. These are basically telescopes with a disk in the middle that blocks out the sun's bright face, allowing you to see the much fainter corona, the sun's atmosphere, around it. These coronagraphs aren't actually designed to study comets. They're meant to monitor solar activity and watch for coronal mass ejections that might affect Earth's technology and power grids. But they've accidentally become excellent tools for observing comets and other objects that pass very close to the sun. So even though 3 I-Atlas was invisible from Earth, the SOHO and STEREO coronagraphs were able to track it throughout its entire perihelion passage. They captured image after image as the comet approached the sun, whipped around it at incredible speed, and began its outward journey. And what those images revealed would absolutely shock the astronomical community. The first really dramatic thing that happened to 3 I-Atlas during its perihelion passage was a massive explosion in brightness. And I'm not exaggerating when I say massive. This was completely unprecedented. In just the few days leading up to its closest approach to the Sun, 3I Atlas brightened by a factor of about 400. That means it became 400 times brighter than it had been just a week earlier. Let me say that again. 400 times brighter in less than a week. To understand why this is so incredibly unusual, you need to know how comets normally behave. As a comet gets closer to the Sun, it gradually brightens for two main reasons. First, it's simply reflecting more sunlight because it's closer to the light source. This follows a pretty straightforward mathematical relationship. Second, the increasing heat causes more ice to vaporize, creating a larger and brighter cloud of gas and dust around the comet's core. For a typical comet making a close pass by the Sun, at a similar distance to what 3I Atlas experienced, you'd expect to see a brightness increase of maybe 10 to 100 times total, depending on how active the comet is and how much ice it's losing. Really active comets with lots of volatile ices might hit the upper end of that range, but 400 times? That's off the charts. Let's compare this to some famous comets to put it in perspective. Comet Hale-Bopp, one of the brightest and most spectacular comets of the 20th century, was visible to the naked eye for a record-breaking 18 months back in 1996 and 1997. It put on one of the best comet shows in modern history. But even Hale-Bopp only brightened by about 100 times at most during its closest approach to the Sun. What about our previous interstellar visitor, Comet 2I Borisov, which is the most direct comparison we have to 3I Atlas, brightened by roughly 50 to 100 times during its perihelion. That was significant and made it easy to study, but it was still well within the normal range for an active comet. So what could possibly cause 3I Atlas to brighten 4 times more dramatically than even Borisov? Scientists have come up with a few possible explanations, but none of them are particularly satisfying. One idea is that 3I Atlas might be unusually rich in what we call highly volatile ices, substances that vaporize at relatively low temperatures. Carbon monoxide ice, for example, starts to sublimate and turn into gas at much lower temperatures than water ice. If the comet has a really high concentration of carbon monoxide, or even more exotic ices like methane or nitrogen, then as it approached the Sun, all of these materials could have suddenly started vaporizing at once, creating an explosive outburst of gas and brightness. Another possibility is that the comet experienced what's called a fragmentation event. Maybe a large chunk of ice broke off from the main nucleus, suddenly exposing a bunch of fresh material to direct sunlight. This newly exposed ice would immediately start to sublimate, dramatically increasing the comet's brightness. But here's the problem with that theory. Observations taken after perihelion show the nucleus still intact and not broken apart, so this explanation seems less likely. There's a third, more speculative idea that involves the comet having a highly layered internal structure. Imagine it like an onion, with a core of very stable material surrounded by layers of increasingly volatile ices. As each layer sublimates away, it exposes the next layer underneath, and maybe each new layer vaporizes faster than the one before it, leading to a runaway cascade effect. But here's what really bothers scientists about all of this: the timing. The 400 times brightness increase didn't happen gradually over weeks or months. It happened suddenly over just a few days. It wasn't a smooth ramp-up that you'd expect from steadily increasing solar heating. It was more like someone flipped a switch. This sudden, explosive change suggests that something specific triggered it. Maybe a particular threshold temperature was reached. Maybe a protective outer crust was breached. Or maybe some other event happened that fundamentally changed how the comet was interacting with the Sun's energy. And remember, this brightness explosion didn't happen in isolation. It was accompanied by something even stranger, a dramatic and completely unexpected color change. If the 400x brightness surge was weird, the color changes that 3I Atlas went through were absolutely mind-boggling. When 3I Atlas was first discovered back in late September 2024, spectroscopic observations, basically breaking down its reflected light into different colors, showed that it had a distinctly reddish appearance. Now, this wasn't particularly alarming at first. Lots of comets and asteroids look reddish because of organic compounds on their surfaces. These organics, similar to the reddish materials we find on Pluto and other distant objects, absorb blue light and reflect red light, giving the object a rust-colored or brick red appearance. The red color actually made perfect sense for an interstellar object. Having spent potentially millions of years drifting through interstellar space, the surface would have been constantly bombarded by cosmic rays, incredibly high-energy particles zipping through space. These cosmic rays chemically alter surface materials over time and create complex organic compounds. This process, called radiation processing, typically makes surfaces redder the longer they're exposed, so a red interstellar object, totally reasonable. But then in early September, observers started noticing something odd. 3I Atlas was turning green, like noticeably green. Now, green is actually a relatively common color for active comets, but it appears for very specific chemical reasons. The green glow comes from molecules called diatomic carbon, that's C2, two carbon atoms bonded together, and cyanogen, which is CN. When these molecules are exposed to ultraviolet light from the sun, they absorb that energy and then re-emit it as green visible light. This process is called fluorescence, and it's the same basic principle that makes a black light poster glow. So seeing 3I Atlas turn green as it got closer to the sun wasn't completely crazy. It suggested the comet was becoming more active and starting to release carbon-rich gases into space. That makes sense for a warming comet. But what was unusual was how quickly and completely the color changed. Over just a few weeks, the dominant color shifted from red to green. We're not talking about a slight green tint appearing while it stayed mostly red. The red color seemed to almost completely disappear and get replaced by green. This rapid transformation suggested one of two things. Either the red material on the surface was getting blasted away really fast, revealing green glowing gas underneath, or something on the surface had fundamentally changed in its chemical composition. Neither explanation is particularly great, because both would require processes happening way faster than we typically see in comets. Scientists were still trying to wrap their heads around the red to green transformation when 3I Atlas did something that left everyone completely stumped. As it approached its closest point to the sun, it turned blue. Blue is not a normal color for comets. Let me show you why this is so weird. The color spectrum goes like this. Red light is low energy with long wavelengths. Green is in the middle. Blue and violet are high energy with short wavelengths. For a comet to appear blue, it needs to be either scattering or emitting way more blue light than red or green light. This can happen under very specific circumstances. When gases get ionized, meaning they've been stripped of electrons by intense radiation, they can emit blue light. Carbon monoxide ions, designated CO+, emit really strongly in the blue and near ultraviolet part of the spectrum. The appearance of blue during perihelion suggested that 3I Atlas was releasing gases that were getting immediately ionized by the sun's intense radiation and all the charged particles flying around. At that distance from the sun, especially during solar maximum, the radiation environment is so intense that pretty much anything released into space is going to get ionized almost instantly. But here's the major problem. For the color to shift so dramatically from green to blue, you'd need an absolutely massive increase in the amount of gas being released. And not just more of the same gas, you'd need the composition to completely change. Think about it like this. When 3I Atlas was green, it was releasing carbon-based molecules that fluoresce green. When it turned blue, it was apparently releasing huge amounts of stuff that could be ionized into blue-emitting molecules. For blue to become the dominant color, completely overwhelming the green, you'd need either an absolutely gigantic increase in total outgassing, or you'd need the comet to suddenly start releasing completely different materials with a totally different chemical makeup. This suggests that as 3I Atlas approached the sun, it either experienced a massive explosive outburst of gas, which fits with the 400 times brightness increase, or it exposed an entirely new layer of material with a fundamentally different composition from what was on the surface before. Natural comets can definitely have outbursts and can change in appearance. That happens. But the specific sequence of red to green to blue over just a few weeks, all coinciding with that massive brightness surge, is completely unprecedented in the entire history of comet observations. Some scientists have half-jokingly pointed out that if you were trying to design some kind of attention-getting signaling system using changes in brightness and color, This dramatic red-green-blue sequence is exactly the kind of thing you might do. Now, that obviously doesn't mean it is a signal. Natural processes can absolutely create dramatic and unusual effects. But it does help explain why this particular sequence of events has raised so many eyebrows in the scientific community. Whatever caused it, by the time 3I Atlas reached its closest point to the Sun, it had transformed into a brilliant blue object, hundreds of times brighter than before, clearly visible in those coronagraph images as it whipped past our star at incredible speed. And that's when it started moving in ways that really shouldn't be possible. After the brightness explosion and the bizarre color changes, 3I Atlas did something that has scientists seriously scratching their heads. It started accelerating under its own power. Let me explain what I mean by that. When any object passes close to the Sun, the Sun's enormous gravity affects its motion in very predictable ways. We can calculate exactly how much the Sun should speed up or slow down an object based on its mass, distance, and velocity. This is basic orbital mechanics. We've been doing these calculations for centuries, and we're really good at it. But anything that moves differently from those predictions falls into a category called non-gravitational acceleration, or NGA for short. This means the object is speeding up, slowing down, or changing direction in ways that can't be explained by gravity alone. In other words, there's some other force acting on it. Now, for comets, experiencing some level of non-gravitational acceleration is actually pretty normal and expected. As a comet gets heated by the Sun, ice on its surface vaporizes and blasts off into space. This is basically like a bunch of tiny rocket engines firing in different directions, and all that escaping gas pushes the comet around a bit. So we always expect to see some NGA with active comets. But here's what makes 3I Atlas so unusual. For the entire time we observed it on its journey through the solar system, from its discovery in September all the way up to its close approach in late October, there was almost zero detectable non-gravitational acceleration. None. It flew in an almost perfectly straight line, following a path that matched gravitational predictions basically exactly. This is actually not normal for an active comet. Most comets wobble around a bit as they release gas and dust and form their tails. The closer they get to the Sun, the more they typically deviate from a purely gravitational path because more material is being released. But 3I Atlas, perfectly straight trajectory, like it was on rails. And then, right at perihelion, everything changed. Suddenly, 3I Atlas started experiencing massive non-gravitational acceleration, way more than any comet we've ever observed. On October 29th, 2024, the day 3I Atlas was at its absolute closest to the Sun, the object was observed to change its direction away from the Sun by about 84 miles. At the same time, it accelerated in its direction of travel by about 37 miles. When you combine these two effects, you get a total non-gravitational acceleration of about 124 miles per day. Now, you might be thinking, 124 miles per day doesn't sound like that much. But remember, we're talking about an object that's potentially 6 miles across and weighs billions of tons. Moving something that massive by 124 miles in a single day requires an absolutely enormous amount of force. Let's compare this to other objects to understand just how extreme this is. Remember 2I/Borisov, our previous interstellar comet? That object showed non-gravitational acceleration of about 62 miles per day at its peak, which was already considered pretty significant. So 3I Atlas is experiencing twice the NGA of Borisov. Or let's look at Comet Hale-Bopp, which I mentioned earlier. Hale-Bopp was a really large, really active comet with powerful outgassing, probably the closest comparison we have from our own solar system to what 3I Atlas is doing. But Hale-Bopp only experienced about 1 to 2 miles per day of non-gravitational acceleration. That means 3I Atlas showed more than 60 times the NGA of Hale-Bopp. 60 times. That's not just unusual, that's completely off the charts. So what could cause this? The conventional explanation is that 3I Atlas must be releasing absolutely massive amounts of gas during perihelion, and all that escaping gas is acting like rocket thrust, pushing the comet around. The 400 times brightness increase supports this idea. Clearly, a lot of material is coming off this thing, But here's what doesn't add up. For gas release to cause this much acceleration, you'd need not just a lot of gas, but gas that's all moving in roughly the same direction. Otherwise, the forces would cancel out. Natural outgassing from a rotating comet tends to be pretty random and disorganized, with gas shooting out from different points on the surface in different directions. To get organized thrust strong enough to push a 6-mile wide object by 124 miles in a day would require something more structured than random outgassing. You'd need jets of gas that are consistently pointing in specific directions, almost like nozzles on a spacecraft. And as it turns out, that's exactly what we see. A few days after 3I Atlas's closest approach to the Sun, on November 8th, NASA released an image that showed something absolutely remarkable. The comet had developed a complex structure of gas jets shooting out from its core. In the coronagraph image, you can see a bright, glowing halo around 3I Atlas that extends outward in every direction for about 310,000 miles. That's a huge cloud of gas and dust. But what's really striking is what's extending even further from that halo. At least 7 distinct, separate jets of gas firing out into space. These aren't fuzzy, vague streams. These are well-defined, structured jets. And here's the really weird part. Most of them are pointing away from the Sun, like you'd expect. But a couple of the smaller jets are actually shooting toward the Sun. That's highly unusual. Let me explain why that's so strange. When a normal comet develops a tail, it's shaped by something called solar wind, a constant stream of charged particles flowing out from the Sun. This wind, combined with radiation pressure from sunlight itself, pushes gas and dust away from the Sun. That's why comet tails always point away from the Sun, no matter which direction the comet is actually moving. You can use Comet Hale-Bopp as a good example. It had a very famous tail, actually 2 distinct tails. One was mostly dust, and the other was mostly gas. The gas tail was lighter and got pushed more by the solar wind, so it extended higher. But both tails pointed in the same basic direction, away from the Sun. That's just physics. So for 3I Atlas to have jets pointing both away from and toward the Sun simultaneously is really unusual. It means there's some force pushing gas toward the Sun that's strong enough to overcome the solar wind. That force would have to be coming from within the comet itself. There's another weird thing about these jets. Their structure. See, 3I Atlas is a rotating object. Based on how its brightness changes, scientists calculated that it spins around once every 16 hours. If you've got random puffs of gas coming from different spots on the surface of a spinning object, the rotation should smear them all together into one big fuzzy cloud or tail. But somehow, these 7 jets on 3I Atlas are distinct and separate from each other. They maintain their structure even as the comet spins. That means these jets must be incredibly powerful and focused, strong enough to blast clear of the comet before the rotation can smear them out. This suggests that the gas isn't just randomly seeping out from the surface. It's being released through specific openings or vents, maybe fractures in the surface, and it's coming out with enough force to create these focused, jet-like structures. Now, before anyone gets too excited, having jets is not completely unheard of for comets. Several comets in our solar system have shown jet-like features, but they're usually much less dramatic, and they don't typically appear in multiple directions at once, especially not toward the Sun. What makes 3I Atlas's jets so unusual is their number, their power, their structure, and their multiple directions. All of these things together create a pattern that doesn't quite match anything we've seen before. But wait, it gets even stranger. Just one day after those images showing the 7 jets were taken, on November 9th, observers captured new images of 3I Atlas, and the whole structure had completely transformed again. Those 7 distinct jets had merged together into what looked more like one giant plume of gas and dust. It extended away from the Sun for almost 1.9 million miles. That's a gigantic structure to appear in just 24 hours, about 8 times the distance from Earth to the Moon. The plume moving away from the Sun looked more like what you'd call a normal comet tail. But even then, it wasn't quite normal. Instead of the typical long fan-shaped fuzzy streak you see in most comet photos, the tail coming off 3I Atlas looked more like smoke rising from a fire, kind of turbulent and billowy. But here's the really interesting part. If you look carefully at the images, there's a second plume of gas coming out in the opposite direction from the large tail. This is what astronomers call an anti-tail, a tail that points toward the sun instead of away from it. This anti-tail extends for about 620,000 miles in the direction of the sun. Now, anti-tails aren't completely impossible in natural comets, but they're pretty rare, and they only happen under very specific geometric conditions. Usually, it's an optical illusion caused by viewing angle. You're seeing particles that were left behind in the comet's orbit appearing to stick out in the direction of travel. But here's what makes 3I Atlas's anti-tail weird. This is not the first time we've seen one on this object. One of the very first unusual characteristics scientists noticed about 3I Atlas, way back in the summer when it was still far from the sun between Mars and Jupiter, was the formation of a sun-facing emission, an anti-tail, when the comet was still really far from the sun, where solar radiation was relatively weak. At that time, scientists thought maybe it was just a quirk of the viewing angle, or maybe some unusual but natural outgassing pattern. But now, months later and much closer to the sun, 3I Atlas is still producing this sun-facing tail. And at this distance, the solar wind is incredibly strong. Any gas or dust should be getting blasted away from the sun with tremendous force. For 3I Atlas to be pushing material toward the sun against that kind of pressure means there's a very powerful process happening inside or on the surface of the comet. The gas jets we talked about earlier could explain it. If you've got focused jets firing toward the sun, they could be strong enough to overcome the solar wind, at least for a while, but it raises the question, why would a natural comet have jets consistently pointing toward the sun? What physical process would create that pattern? There isn't an obvious answer. The combination of the bright halo, the 7 jets firing in multiple directions, the massive tail, and the persistent anti-tail all together create a picture of an object that's releasing gas in a highly organized, almost structured way. And that's not really how natural outgassing is supposed to work. All of this extreme behavior, the brightness surge, the color changes, the powerful jets, the massive non-gravitational acceleration, tells us something important. 3I Atlas must be significantly bigger than we initially thought. There's been a lot of debate in the scientific community about the actual size of 3I Atlas. I'm talking about the solid nucleus itself, not the huge cloud of gas and dust surrounding it. Early conservative estimates put it at maybe 3 miles across at most, possibly even smaller. But given everything we've observed, those early estimates are probably way too low. More recent calculations, taking into account the massive amount of material this thing has released and the fact that it's managed to stay intact through all of this, suggest 3I Atlas is probably more like 6 to 7 miles across. That might not sound like a huge difference, but remember, we're talking about a 3-dimensional object. If you double the diameter, you actually increase the volume by 8 times. So a 6-mile wide comet has 8 times more material than a 3-mile wide comet. This larger size estimate makes 3I Atlas truly massive compared to our previous interstellar visitors. Oumuamua was probably only about a quarter mile long, so 3I Atlas would be roughly 25 times larger than Oumuamua in diameter, even compared to 2I Borisov, which was already considered pretty big for an interstellar object at about 1 mile across. 3I Atlas is 6 times wider. That means it could have over 200 times more volume and mass than Borisov. This massive size is important for several reasons. First, it helps explain how 3I Atlas has been able to release such enormous amounts of gas without breaking apart. A bigger object has more material to lose and can handle more stress without fragmenting. Second, it raises a really interesting question about probability. The bigger an object is, the more likely it is to collide with something during a journey through interstellar space. Space is mostly empty, sure, but over millions or billions of years, even rare collisions become probable if the object is large enough. Think of it this way. A small object is like a bullet flying through space. It's got a tiny cross-section, so the chances of hitting anything are very low. But a large object is like throwing a beach ball. It's got a much bigger cross-section, so the odds of hitting something go way up. For something as large as 3I Atlas, to survive a journey of potentially millions of years through interstellar space without getting destroyed by collisions is actually pretty unlikely. Not impossible, but unlikely enough that finding an object this large is somewhat surprising. And then there's the timing to consider. This object just happens to fly past our sun at a moment in human history when we have the technology to detect it, track it, and recognize it as an interstellar visitor. The universe is about 13.8 billion years old. Modern astronomy is only about 100 years old. The window of time when we've been capable of detecting interstellar objects is only about 10 years. So for an object this rare and this large to show up right now during our tiny slice of cosmic history is remarkably fortunate, or remarkably suspicious, depending on your perspective. Let's take a step back and compare 3I Atlas to our two previous interstellar visitors to really understand just how unusual this object is. Oumuamua, our first confirmed interstellar object, was definitely weird. It had that strange, elongated shape, the high reflectivity, and the unexplained acceleration with no visible outgassing. These features led to significant debate about whether it might be artificial, though most scientists ultimately concluded it was probably just an unusual natural object, possibly a fragment of a nitrogen ice planet similar to Pluto. But here's the thing. Despite all the strangeness, Oumuamua was inactive. It didn't have a tail. It didn't show obvious signs of releasing gas. It was basically just a weird-shaped rock tumbling through space. Strange, yes, but in a passive way. 2I/Borisov was the complete opposite. It was totally normal. It looked like a comet, acted like a comet, had a composition similar to our own solar system's comets, and behaved exactly as we expected throughout its entire visit. Borisov was actually reassuring because it suggested that most interstellar objects would be familiar and understandable. 3. I-Atlas combines the weirdness of Oumuamua with the activity of Borisov, but then cranks everything up to levels we've never seen before. It's got the massive brightness changes, the bizarre color transformations, the extreme non-gravitational acceleration that exceeds even Borisov by a factor of 2, the structured gas jets pointing in multiple directions, the persistent sun-facing tail that shouldn't exist. Every single one of these features individually could potentially be explained by some unusual but natural process. Maybe it's a comet with an unusual composition, maybe it has a weird internal structure, maybe we just got unlucky and happened to observe it during a series of random outbursts. But when you add all of these unusual features together, all happening to the same object at the same time, it starts to strain the bounds of coincidence. It's like if someone walked up to you and said, "I just flipped a coin 10 times and it came up heads every single time." Sure, it's technically possible. Probability says it should happen once every 1,024 tries. But if you actually witnessed it, you'd probably start to wonder if something else was going on. That's kind of where we are with 3I Atlas. Each individual feature might have a natural explanation, but the combination of all of them together is so statistically unusual that some scientists are starting to ask whether we should at least consider alternative explanations. Okay, so here's where we need to talk about the elephant in the room. Could 3I Atlas be artificial? Could it be some kind of alien probe or spacecraft? Now, before anyone starts rolling their eyes or adjusting their tinfoil hats, let's be clear about something. The vast majority of scientists studying 3I Atlas believe it's a natural object, probably just a really unusual comet with some rare properties that we don't fully understand yet. That's the consensus view, and it's based on sound scientific reasoning. But there is a small group of researchers, including some very serious and respected scientists, who think we should at least consider the possibility that 3I Atlas might not be natural, and their arguments are worth hearing. The case for artificial origin basically comes down to 3 main points. First, the behavior. If you were designing a spacecraft or probe for interstellar travel, you'd want it to be able to accelerate and maneuver without using chemical rockets, which are heavy and inefficient. Instead, you might use something like an ion drive or a solar sail. Technologies we're already developing ourselves. An ion drive works by shooting out charged particles at very high speed. From a distance, that would look exactly like jets of gas coming from different points on an object. The non-gravitational acceleration we're seeing could be explained by periodic firings of such a propulsion system. The color changes could potentially be explained by different types of emissions from different engines or systems activating as the object passes through different regions of space and encounters different conditions. Second, the timing. This is admittedly more speculative, but some researchers have pointed out that 3I Atlas arrived at our sun during solar maximum and during a period when humanity has radio telescopes, space-based observatories, and the ability to recognize interstellar objects. If you wanted to survey a solar system and study a technological civilization, arriving when the star is most active and the civilization is most detectable would be logical. Third, the sheer statistical improbability of everything we've observed. Yes, nature can produce unlikely coincidences, but at some point, when you keep adding unlikely things together, you have to at least ask whether there might be a simpler explanation. Now, let's talk about why most scientists reject this hypothesis. The main argument against artificial origin is Occam's razor, the principle that the simplest explanation is usually correct. We know comets exist. We know they can behave strangely. We know that nature is full of unusual phenomena we don't fully understand yet. So the simplest explanation is that 3I Atlas is just a weird comet, and we'll eventually figure out the natural processes causing its unusual behavior. Additionally, if 3I Atlas were artificial, we'd expect to see certain features that we're not seeing. For example, we'd probably expect more regular, organized behavior. We'd expect the engines to fire in patterns that made obvious sense for maneuvering or course correction. What we see instead is somewhat chaotic and doesn't seem to follow an obvious pattern. There's also the lack of any clear technological signals. We've pointed radio telescopes at 3I Atlas and haven't detected any radio transmissions or other obvious signs of technology. That said, the absence of radio signals doesn't prove anything. A sufficiently advanced civilization might not use radio at all, or they might be using communication methods we can't detect or don't recognize, or the object might be a probe that's not actively transmitting. Here's my take on this. Extraordinary claims require extraordinary evidence. Saying that 3I Atlas is an alien probe is an extraordinary claim, and while the object is certainly unusual, unusual isn't the same as impossible. We need much stronger evidence before we seriously consider artificial origin, but, and this is important, we shouldn't dismiss the question entirely. Science progresses by asking uncomfortable questions and following the evidence wherever it leads. If 3I Atlas continues to behave in ways that can't be explained by any known natural process, then at some point, we have to at least seriously consider alternatives. The good news is, we're going to get another chance to study this object very soon. So where does all of this leave us? What happens next with 3I Atlas? Right now, as I'm recording this, 3I Atlas is moving away from the sun, heading back out into the outer solar system. It's still bright enough to be observed by our most powerful telescopes, both on the ground and in space. Scientists are continuing to track it, gather data, and try to make sense of everything we've witnessed. The big upcoming event is December 19th, 2024. That's when 3I Atlas will make its closest approach to Earth. Now don't worry. Close is a relative term in space. The comet will still be millions of miles away, nowhere near close enough to pose any danger. But it will be close enough that our most powerful Earth-based telescopes will get their best views yet. During this flyby, astronomers are planning to use everything we've got. The Hubble Space Telescope, the James Webb Space Telescope, major ground-based observatories around the world, they'll all be pointing at 3I Atlas, gathering as much data as possible. We'll get detailed spectroscopic data that should tell us more about what this thing is made of. We'll get high-resolution images that might reveal details about its nucleus that we can't see right now. We'll measure its exact trajectory and acceleration with unprecedented precision. And if there's any sign of technological activity, heat signatures, regular patterns, any kind of signal, this will be our best chance to detect it. After the December flyby, 3I Atlas will continue on its path out of our solar system. Within a few months, it will have moved beyond the orbit of Mars. Within a year, it'll be past Jupiter. And within a decade or so, it will fade from view entirely as it leaves our solar system and returns to the darkness of interstellar space. Unlike Oumuamua, which we discovered too late to mount any kind of mission, there has been some discussion about whether it might be possible to send a spacecraft to intercept 3 I-Atlas. Unfortunately, the answer is almost certainly no. The object is moving too fast, and by the time we could design, build, and launch an interceptor mission, 3 I-Atlas would be long gone. So we're left with remote observations. We have this one window of opportunity to study this mysterious object, and then it vanishes forever, carrying its secrets with it back into the void. The data we're gathering now will keep scientists busy for years. Every observation, every spectrum, every measurement will be analyzed and reanalyzed, looking for clues about what 3 I-Atlas really is and where it came from. So what's the bottom line? What should we take away from all of this? 3 I-Atlas is, without question, one of the most unusual objects ever observed by astronomers. Whether it's the strangest comet we've ever seen or something else entirely, we're witnessing something truly remarkable. The object has challenged our understanding of comets, tested the limits of our observing capabilities, and raised profound questions about what else might be out there in interstellar space. Every assumption we had about interstellar objects has been called into question. Is it an alien probe? Probably not. Most likely it's just a really weird natural object that we don't fully understand yet. Nature has surprised us countless times before, and it will surprise us again. But could it be artificial? We can't completely rule it out. And that's actually kind of exciting. Even the tiny possibility that we might be observing a manufactured object from another civilization is thrilling and humbling at the same time. What we can say for certain is that 3 I-Atlas has taught us that interstellar space is full of surprises. The 3 interstellar objects we've detected so far, Oumuamua, Borisov, and Atlas, are all different from each other. Each one has taught us something new, and they're probably just the tip of the iceberg. There are likely thousands of interstellar objects passing through our solar system every year. We just can't see most of them because they're too small, too dark, or moving on trajectories that keep them far from Earth's orbit. As our detection capabilities improve, we'll find more of them, and each one will add another piece to the puzzle of what's out there in the galaxy. The next few weeks will be crucial. The December flyby might answer some of our questions about 3 I-Atlas, or it might raise entirely new ones. Either way, we're living through a genuinely historic moment in astronomy. So keep watching the news. Keep an eye on what NASA and other space agencies are reporting. Because whatever 3 I-Atlas turns out to be, strange comet, rogue fragment, or something we haven't even imagined yet, it's given us a glimpse into a universe that's far stranger and more diverse than we ever knew.